Welcome. Let me tell you about a theorem in the partitions of numbers, which I discovered as a high school student more than 40 years ago. And I had a lot of fun thinking about this also with these Cuisenaire sticks and with the help of a computer using basic programming language. The theorem is here. It's a recursion formula for the partition function Pn can be written as a sum of the smaller Pn minus k, where sigma k is the sum of the divisors of k. And I thought about this geometrically using area. The area here, these are all the partitions of the number 6. You can write this as a sum. You can split this up and you can look at when does the first time 1 appear, when does the first time 1 or 2 appear, when does the first time 3 or 1 appear, 4, 2, 1 appear. And in each case this comes with a smaller partition. For example, 7 times 2, 4, 6, 7 times 1 appears here first. These are the 7 partitions of 5. And then here, when we look at the next thing, there are 1, 2, 3, 4, 5 partitions. There are 5 partitions of 4, and so on. So what we do is we decompose this rectangle, this partition rectangle, into smaller, into parts, and we count things. I did not actually kind of visualize this like this as a student. I must have thought about it like this, but this is what I wrote down in that paper, or that work for Schweizer Jugendforscht. So what we have is, let's call Pn this block, and the area of this is n times Pn. And now we write things up. I proved the lemma, which I didn't call lemma, but that's kind of a lemma. The number of sticks f in this Pn is the number of sticks f in Pn minus f, in a kind of, and we have taken away these sticks, and plus Pn minus f. So it's a recursion, and a recursion formula, and then you can write this, iterate this. So we write this again using this lemma, and we get then the number of sticks in Pn is a sum of smaller partitions. And then we write this down like that. I wrote this down in an array, and then you look how many times does each term appear. For example, the term 3 appears here and here because there's a factor 1 and a factor 3. 4, 2, 1. There would be 5 and 1. So you just count the number of times that it appears, and then you summarize it together and you get that nice formula. So nowadays, I mean, if you look up, you Google it, kind of about partition functions and sigma things, so you find that this can be proven just by taking the derivative of that. If you take the derivative of this, k times pk, you get areas here as the coefficients. And then you just look what happens here on the right hand side, and you look at the combinatorics, what you have on the right hand side, and you are done. So that's the proof I wrote down. This is a little bit of history about this result. But what was actually for me much more important than the discovery, I had a lot of fun of course, but was the process or scientific process when you are kind of doing something. And so I make here kind of 3 remarks about the sociology of science. First of all, it very much is important how fancy a topic is. This topic is, you know, was fancy more than 100 years ago. This was the fashion of the time. Nowadays it's no more fancy. I myself did not learn that in college, except partitions I of course learned about in the context of representations of the symmetric group there, but we didn't look at the combinatorics of the partition functions, and so you would need a more sophisticated combinatorics course. But even many combinatorics courses don't mention this. So fashion really matters. And then also it comes with the next thing, with the evaluation thing. Of course, if you have not a fashion subject, there are also less experts who can really judge this. But also appearance matters, so this kind of things, my presentation looked like a kindergarten thing, right? I was working with the sticks which a kid works, so you automatically, even if you are a professional mathematician, I was also judged by one professional mathematician. The first judge had no idea even which topic it belongs to. He didn't know about additive number theory, had absolutely no clue. And the second was a professional mathematician who has published papers, but it was not his speciality. But he could not put it into context. And I think this would have deserved more than just a B grade. I got a B grade. Very good is actually a B grade. So there is outstanding, which is kind of an A grade, but that was judged as a B grade, and that was only one of many results. I had also the pentagonal number theorem I independently discovered. I used it for recursion, and that was one of the results I could not prove. But I had many more results. This was actually a very important lesson. Evaluation is a lottery. I myself have been over-evaluated at some times. I've also been under-evaluated at some times. So it's a matter of luck whether you have somebody who really can understand. I mean, Ramanujan, I don't want to compare myself with Ramanujan, but Ramanujan came from a humble origin, and he had the luck that there was somebody, Hardy, who could really see what is happening, what kind of values are in this completely independent work. As a matter of fact, the judgment is hard. I have 3 papers still in my desk which I have to referee, and I don't know, it takes a day or two, you know, to do it, maybe to replicate the results, reprove the results. It takes a lot of time, and you have to do a lot of research to evaluate something, even if it's in your expertise. Peer review also completely broken, and the reason is clear. It's too easy to write articles. There are too many mathematicians who write articles. So you can essentially write an article as a kid very fast. And who judges this? Where are the experts who can judge this? So maybe this can be solved by giving more incentive to peer review, give more credit to the reviewers. I think personally, every paper which has been refereed, the referee report should be included. And so it also should be included when it is rejected. Maybe publish it and say why it is rejected. And there is also a lot of hype and hubris. This is especially the case in subjects where money is involved, like grants, or subjects which cost a lot, like high energy physics. You need to lead the public to support the thing. Mathematics is, with respect of this, quite good, but it comes with a prize, and the prize is that discovery is not counted. In chemistry, if you discover a new compound, or in astronomy, if you discover a comet or an exoplanet, that's a big thing. In mathematics, if you discover a theorem, it's nothing. And the reason is that it's cheap. Mathematics doesn't cost you anything. But that's what I wanted to say today.